At this moment, we are talk about the Fourier series. Fourier series, the meaning of Fourier series is okay. If xt is periodic, it has a period t0, and the inverse of them is a fundamental frequency. If it is periodic, then xt can be expressed by the linear combination of complex exponential. It says that this one, some k should be changing over minus infinity to the infinity, and ck times exponential j k omega 0 t. Okay, this says that if xt is periodic, and it means that it has period t0, then xt can be expressed by the linear combination of a complex exponential. And another constraint, if x is a real, xt is a real signal, then we can express that one into this way: xt I equals to a0 plus some k should be starting from 1 to infinity. Starting from 1 to the infinity, and ak cosine and omega 0 t. Nth harmonic component is this one. At this moment it should be k. Okay. K is a time, it's a sweeping variable, and plus some k to the infinity. K should be starting from 1, and the bk times sine k omega 0 t. So this is the Fourier series that we talk about. If xt is a periodic, then xt can be expressed by the linear combination of complex exponential. And at this moment, the k starting from minus infinity to the infinity. Okay, and if another constraint is xt is periodic and xt is a real signal, then xt can be expressed by these the expressions. In this case, we change the cosine and sine the basis functions. So at here, a0 is a DC component, a0 equals to c0. You can we already talked about how to calculate ak and bk. This is the Fourier series statement. Okay, if any periodic real signal can be expressed by the linear combination of cosine and sine, it's a harmonic frequency. Okay, so how many components are contained in the signal is also found from this coefficient. The Gibbs phenomena says that if we increasing the more harmonic components, if there is some discontinuity, you can see here there is a 2 discontinuity shown here. In that case, at the discontinuity region, it always passing the half of the value. It means at this moment this is 1 and 0, then it passing through 0.5, and there is some non-converging point that is called Gibbs phenomena. To explain that one, I would like to show you that what does that mean. So to show you that, I would like to use a Python code. First, this one is a Fourier series. We know that the rectangular first. We already solved this one at homework 7. First, I would like to import numpy, and to plot that one, plotting tool imported, and I defined the t0 as 1.0, so it's the same as we have done in the at here. This is t0 is 1 and f0, like that. So I would like to do that. f0 is 1 over t0, and omega 0 mp dot 2 times pi times f0. Okay, and for the sampling, I would like to use t0 over 20. Okay, and the fs is 1 over ts. Okay, this is a sampling frequency. So that is the same we have done over here. Okay, so that is defined first, and then I need to define the time series. Time series, you can see here that we are using this time series. Okay, I would like to define that one on here. I would like to use MP linspace. I specify the starting point is -1 and the ending stop is up to 2 seconds, -1 second to up to 2 seconds, and number of point is integer. That I have 3 seconds. 3 seconds divided by sampling times. I have to take an integer part of that, and one more number should be added to include the end point. So end point true. So if you write down this way, then that gives this variable up to here, -1 to 2 seconds. Okay. Then I would like to calculate the xt. Okay, let's access. How are we gonna do that? Obviously, it's a list. I would like to calculate these values. Okay. In case of negative and positive is a different patterns. How are we gonna generate that one? Okay, to generate that one, I think I need to define a function fxt. It takes a time, and if I define some fractional number can be obtained this given t minus integer part of t, then we have a fractional part. Fractional parts are assigned at t. If TMP is less than -0.5, then that is should be 1. And else if TMP is less than 0, then it should be returned 0. Else if TMP is 0.5, then it should return 1, else return 0. So this is the function that generating 1 or 0 rectangular pulse can be generated. So I would like to use this function t for all time in TS. Okay, by use of this function, we can create this rectangular pulse. So okay, we can drop out this one. So I would like to plot this one first, and then I create the TS and XS. Then I think I can plot the result. So to plot that one, I need to use a plotting panels. So figure size 10 by 6. Okay, and the first plot fig add subplot 2 1 by 1. First one 2 by 1 figure, and the first one is this one. So x1, I would like to plot TS and XS, and grid A and show. Maybe this one is a okay, it's a related 0.7 format. So I can change the path over here. Okay, let's try to plot that one. Okay, it shows this graph as we expected. It is a rectangular pulse. It's the same as in Excel. We already plotted the time domain pulse. It's the same. Okay, it's the same graph with Excel, and I would like to plot two graphs. I selected the 2x1 graph. The bottom one, I would like to plot the spectrum. Okay, anyway, at this moment I generated okay, close up. Okay, I generated the time sequence and the XT sequence. I got that one, and I would like to plot the Fourier series result. You know that we need to add up the harmonic component as we have done at here. You know that we added accumulated the nth harmonics. DC, first, third, fifth, seventh, and ninth. That harmonic component should be added up to plot like that. So to plot this kind of the Fourier series result, the approximate of the rectangular pulse, because we truncated up to 9th harmonic only. So I would like to add up the harmonic component to plot the Fourier series result. So to plot that one, I defined the nth harmonic sequence like xn. Okay, here. It means that it is add up the DC first, third, like that, nth harmonic component are added. First, it is a 0.5 in DC component 0.5. So I added in. This one means that the DC component are generated like that. So all the way down, this DC component is all the way 0.5. That is shown here. That's this one. And then I have to think about the nth harmonic. Nth harmonic starting from the DC component. So that's this one. And HN, at this moment, the DC component has a 0.5, magnitude 0.5. Okay, so I think this one is better to understand. XN is HN current value, and for T in TS. Okay, and then I can test for run. It's okay. So then at here I can plot that one all the way 0.5. Okay, this means that this column DC component, I added a DC component here, and I need to add nth harmonics like this way. So to add nth harmonic, I can try that one into this way. Range first harmonic to the 9th harmonic by 2. If you're using in this way 1, 3, 4, 5 and up to 9, so by adding the 2 steps, so starting, stop, and step. So if you're taking this approach and we're taking 1, 3, 5, 7 like that, is other harmonic component will be added, and HN append. So I think the coefficient is 2.0 divided by n divided by pi. Okay, this one means that this component is 0.5. The DC component is 0.5 as shown here. Okay, and I need to calculate each component according to the n. This n is changing in these patterns. Firstly, let's try this one. If you try this one, then okay, it will be one first and third harmonic only. So if I taking this way, then it takes only one. Okay, sinusoidal one like that. So this one is just the coefficient of this sinusoidal sine wave coefficient. Okay, that is the Bn. That's this one. Okay. And I added the harmonic component here. Nth harmonic should be added, and xn, this sequence should be accumulated. Xn plus hn current value amplitude times sine n times nth harmonic ts. Then this operation corresponds to this kind of accumulation. You know that previous data is added and the first harmonic, and here D12 means first DC and first harmonic and added the third harmonic, like that. That is accumulated in these patterns. Okay, you can see here. There is also accumulated in that pattern. So that is coded like that. Okay, then I have xn. Xn at this moment is up to 1 only. So in these cases, DC and first harmonic is added here. So I can plot xn. Then I can compare the rectangular. Okay, at this moment I can. It would be looks like this one because it contains only first harmonic. So this one is blue one is rectangular, and red one is a first harmonic component. So if I taking this range, then that will be the same as this one. Let's try to run that one before save and run. Okay, there is a okay. I have to attach the numpy package and then run. Then I have this graph. That's the same as this one. What about we plot up to 9th harmonic? Then we will have this one. To get that result, we have to increase this amount of harmony. Then range will span 1, 3, 5, 7, and 9 up to 9. So that will be the same as we have done in Excel. That's this one. Okay, that's it. You can compare these two graphs. Okay. Okay, this one and these two things are plotted the same things. Sampling time is the same. But if we increase the number of samples, like 100 point, then that is much smoother. Okay, you can see some smoothing functions. The Gibbs phenomena that talk about here, the discontinuity point exists, then there are, at the discontinuity point, the overshoot level does not becomes the zero. It means there is some finite mismatch exists at the discontinuity point. You can see here there is some overshoot. You know that maximum rectangular pulse has a maximum is 1, but the Fourier series has more than 1. It is about 9% is larger. To see the Gibbs effect, we can increase the number of the harmonic component. Like let's try this one. Then we can firstly let's see this one first. We already learned and find out the overshoot levels exist at the discontinuity point, and you can see that at the discontinuity point, at this point, it's passing through 0.5 and 0.5. Okay, that's passing the half of the discontinuity value, 0 and 1. That half is 0.5. That's passing here, and there is some overshoot that exists. At this moment, we add up to 9th harmonic. But if we're increasing this one, then 19th harmonics are added. 19th harmonic added. In that case, you can see still there is some overshoot exist here. So this mismatch is called the Gibbs phenomena. The Gibbs phenomena says that even though we increase the number of harmonics, at the discontinuity point there is some finite mismatch exists. But but it's not that problem. If you're increasing in n is large enough, then this energy of the mismatch is very small, so it doesn't matter when we practically use. So you need to know that what is the Gibbs phenomena. Gibbs phenomena says that even though we increase the number of harmonics, still there is some mismatch between it still has some mismatch at the discontinuous point. So that is called the Gibbs phenomena. Lastly, I'd like to plot the spectrum of the signal in the Python. To plot the spectrum, I add one more axis. So the second plot is a fig, add subplot 2 by 1 and the second one. I can plot that one by use of stem. Stem can plot this kind of vertical spectral contents. So that is actually designed to plot the digital signal. So at this moment the frequency is Fn. So frequency is Fn, and the contents of Fn is the harmonic amount of harmonic component is Hn. So Fn and Hn are plotted, and marker format is arrow. Okay, then I can try that. Run this one, and then we can have this plot. The x-axis is the frequency, but the above one is time domain, but the bottom one is the frequency domain. In the frequency domain, this says that the DC component, that's about 0.5, and the first harmonic is a 0.6 something, so that's 0.69. So that is 0.69 is this one, and there is no second harmonic, third harmonic, fifth, seventh, 9th, 11th, like that. This shows the spectrum of this Fourier series component. So we studied about how to understand the Fourier series and how to interpret that one. And also by use of Fourier series, you can plot the same signal in the time domain or in the frequency domain. So we need to we can interpret the spectrum domain. What does this mean? This spectrum domain graph looks like this time domain graph. Okay, both we have two different the plotting method in the time domain or spectrum domain. We can transform by use of Fourier series.